Welcome back from spring break. I hope it was a good one. Mine was great. I enjoyed it a lot. We're going to do a little review of the conics that we talked about before break, and then we'll get into hyperbolas today. And then I will meet you at our Zoom meeting at 9 o'clock. So let's please make sure you're taking notes so that when you ask questions at the Zoom meeting, we have a mutual frame of reference. So we talked parabolas. And by the way, do you remember when we discussed Cornell notes in the beginning of the school year and y'all decided you didn't like them? This might be the perfect time to utilize them because while you're watching, you have your little left-hand column over here. You can write down your questions so that when we are together in Zoom, you can ask those questions and you know what you can remember those questions are as you're watching this. All right, parabolas. Parabolas were of the form y equals a times x minus h quantity squared plus k. And the other version is x equals a times y minus k quantity squared plus h. So it depended, this would be an up-down opening if a is positive or a is negative. And this is a left-right opening if a is positive or if a is negative. All right, and then we had a general version of these. The general form would be ax squared plus bx plus c. This would be the y equals version of it. In order to put the general into the standard, you would need to employ completing the square. All right. Then when we looked at a parabola on a coordinate plane, let's say that would be the vertex. So the coordinates would be hk. Then there was the focus up here, and then the directrix down here. And then there is a line that is perpendicular to this axis of symmetry, and it goes through the focus perpendicular to the axis of symmetry and hits the parabola. And the name of this line, the latus rectum. And then there's a bunch of distance relationships in here. So the distance from the focus to the vertex is the same as the distance from the directrix to the vertex. And that distance is 1 over 4a. And then the distance from the focus out to the parabola is 1 over 2a. All right, so that covers parabolas. And then we've got circles. Circles were the easy ones. Circles. So a circle had the general form of x minus h quantity squared plus y minus k quantity squared equals r squared. So that's really just a very fancy version of the Pythagorean theorem. All right, if we look at a circle on a coordinate plane, the center is at hk, and then this is our radius. And so sometimes you would be given a point on the circle in the center. In order to find the radius, you would have to use the distance formula. So you would have to do, that's a 1 squared plus y1 minus y2 quantity squared. That's a 2. And that's equal to your radius. So again, this is just another fancy version of the Pythagorean theorem. So circles were nice. Those were fairly straightforward. And then we got into the ellipse. All right, so ellipses. The ellipse gave us the form x minus h quantity squared over a squared plus y minus k quantity squared over b squared equals 1. And so you'd have an ellipse on a coordinate plane, and the center would be at hk, and then you would have the two foci, and 2 vertices. And then up here and down here, those were the co-vertices. So the length from the center to a vertex, that length we called A. The length from the center to a co-vertex, we called that length B. And the length from the center to a focus, we called C. And there was that Pythagorean relationship here as well. So in this case, we have B squared plus C squared equals A squared. Which makes sense, right? Because A is the longest. So if you took these 3 segments and you made a right triangle out of them, this would obviously be your hypotenuse. Okay, so that's our ellipse. And then hyperbolas will be next. So I'll put that in a different segment.